Sounds good.
Okay, all set. So first of all, it's a pleasure to meet you in person. I know that we've been talking throughout the throughout both semesters, but it's good to finally speak with you in person, or at least virtually.
Oh, yeah, more or less in person.
Absolutely. So we or took the liberty of putting together a presentation for you. It's just going to kind of go over the
Oh,
vehicle at a high level. So if you think that this would be a good place to start, we could do that. Or if you would prefer, we can jump straight into kind of the review of the vehicle. Which would you prefer?
go ahead and go through the presentation.
Okay, sounds like a plan. So we will jump over to the first slide.
Hmm.
Okay, so to do quick review, the category that we're going to be competing in is the 10K COTS category. So the core objectives for the team this year are mainly really honing that flight performance and making sure that we're as consistent as we can possibly be and be able to predict it with high degrees of accuracy, as well as making sure that we have a completely nominal and successful recovery. So part of the ways that we're going about doing this is increasing our off-the-rod velocity to increase stability. In terms of our vehicle last year, we observed that like with the higher wind speeds at the launch site, um, it ended up throwing off our simulations and creating off-nominal conditions. So one of the ways that we're going to try and remediate this is to increase that off-the-rod velocity. In addition, we're going to improve our recovery systems against failure modes that we've experienced in the past, things like reducing possible snag points on the recovery harness, reducing any cutting points, etc. We're also going to,
Okay.
or we have been improving our SRAD tubes and winding processes. So trying to make them both more aerodynamic and also as weight reduced as possible. So the rocket also features some very interesting stuff this year, both new and continuations from things in previous years. The first is that we are flight testing our fully SRAD flight computer. We call this the backplane. So if you hear that in reference as we go through the presentation, this is what we're referring to. We also have an SRAD reefing system, which will be demonstrated on the payload. Very excited about that. We'll dive into more details on that in just a moment. And in terms of trying to, in our pursuit of gathering new flight data and trying to analyze our flights better, we've come up with a new system to try and measure whether or not our BP detonation pressures and the shock force analysis are consistent by creating a load sensing bulkhead, which we'll dive into more details on in just a moment. So going on to the next slide, please. Oop, there we go. So to do a quick concept of operations, most of this is as you'd expect, but to kind of go over some of the main points. So immediately upon boost, we've got several different SRAD boards, which are doing data collection on both. There's two separate things. It's the actual load sensing bulkhead that we just alluded to, and also some boards on the payload called Grim Reefer. So those will start collecting data and will emit the Fox Hunt trackers for additional methods of recovery as well. So that's right on boost. We have an M3400 motor from Cicerone powering this rocket, and the burn time for that lasts around 3 seconds. We'll coast the rest of the way to our apogee, which currently is projected to be around 12,000 feet. And
Backing up 1 second.
Sure.
You actually have that motor in your possession.
No, we don't have that motor. So we've purchased it with one of the authorized vendors that Ezra provided, and that will be shipped to the competition where we'll pick it up and assemble it on site.
So you've established they actually have the motor.
Correct. We've
Okay.
already purchased it, and we've asked them to send it over to Spaceport America. So we should be, we're following the instructions that Ezra has provided on that regard.
Okay. I ask because there's some supply issues with Cicerone motors at the moment, and
Gotcha.
want to make sure that the motor you think you're using actually exists.
As far as we're aware, it does exist.
Okay.
We'll follow up just to make sure that the shipping and all that is going correctly. But to the best of our knowledge, we've purchased that back probably upwards of January or December at this point, and it's been hopefully all good for a while now. But we'll
Okay.
double check on that just to double check. But continuing with the concept of operations. So once we nose over the onboard COTS electronics, which control the main flight events, in this case, we're using RRC3s. Those will fire a black powder ejection charge, which will separate the vehicle. We are using a single bay dual deployment recovery system. So we'll have a streamer that pops out, which will provide the majority of the aerodynamic drag to slow down the vehicle. And once we reach that 1,000 foot AGL, we will pop some tender descender twos, and that'll fully unfurl our main chute and allow us to descend at a safe rate. The payload will be ejected separately, and as per the reefing system, it'll have its own mission, but instead of deploying at about 1,000 feet, that will unreef and fully expand its chute at about 2,000 feet. But without further ado, we'll dive, that's kind of like the overarching mission objectives, and we'll dive straight into some of the more vehicle-specific information.
Okay, so to give an overview of the structural composition of our rocket, we're using a combination of fiberglass and carbon fiber body tubes. We have 3 tubes on our rocket. The upper 2 are fiberglass and the lower 1 is carbon fiber. All 3 of these tubes we're making in-house with a filament winder with composite toe. We're using 3 layers of 60-degree winds just to give us strength in both the hoop and axial directions. And we've been working on this for a few years, and our big goal this year was just to continue improving our surface finish, which I think we've successfully accomplished. If you have any more specific questions about our tubes, though, I'm happy to answer.
Not at the moment.
For our nose cone, we're doing a fiberglass layup. We've experimented with a couple of different types of molds over the last few years, and we've settled on this 3D printed clamshell mold. So we basically 3D print each half, and we do a number of steps to prepare the inside surface to get it nice and smooth. And then we do a fiberglass layup to get the bulk of our nose cone there. We're using fiberglass because a portion of our avionics base sits inside of the nose cone, and we don't have any external antennas, so we want it to be radio transparent. Only the tip of the nose cone is made of aluminum, and that's just because it's hard to get that fine point with the mold itself.
I am curious. You mentioned same manufacturing method as Kong's nose cone. I'm not familiar with them.
I'm sorry. Kong is our rocket from last year.
Oh, okay.
For our fins, we're using a water jet to cut carbon fiber sheets, compressed carbon fiber sheets. We're using 3/16 thickness, which we've calculated to provide adequate safety at our predicted speed. These have an integrated fin tab that slots through holes that we've drilled in the booster, and it fits into a fin support structure that we have a few slides on coming up. Yeah, might as well jump right into those.
Let's say you mentioned that the thickness was going to be adequate. Is that based on what, fin flutter or?
Yep. We have some analysis slides coming up later in the presentation that talk about that. But yeah, it's a fin flutter velocity.
But let me jump ahead. I remember on your second report, you were using the fin flutter formula from Apogee.
Yeah.
Yes.
Which turned out to have an error.
Yeah, I'm gonna let Donovan hop in here. He's our analysis lead.
So we looked at the new article that was published from December with the corrections, and they had the correction of the factor of square root 2. There was also the correction of a constant that was not actually a constant and depended upon fin geometry. And what really affected that was the sweep length. So we had to redesign our fins a little bit and make the sweep angle less aggressive. And changing that and using that new formula, going through that article. The stuff you see here on this slide is I built a new sheet for it just to make sure and verified it separately. So this is with the most up-to-date information and those corrections.
Okay. Thank you.
So hopping back to the fin support structure, like I mentioned, our water jet cut fins have tabs on the ends, and these slot through holes in our booster tube and into this series of interlocking rings and bars that were also water jet cut from carbon fiber. And this just provides additional bonding area for the epoxy that we use to join the fins. And it also helps us get a nice 90-degree alignment and 90-degree offset between the fins. For our boat tail, we use this at the aft end of our carbon fiber tube. It slots into the end, and then those little tabs that you see on the forward end are actually part of the fin support structure, so they interface with those bars. And this just creates a very rigid assembly at the aft end of the rocket. It also tapers down to, I think it's 4.5 inches, and that fits into our thrust plate and motor retainer, which we machine from aluminum. I don't think we have a slide on those in particular, but fairly standard.
let's see, it's PETG. How is it attached?
So you can see it has an integrated shoulder at the top end there. That slides into the booster tube. It gets epoxied in place. But like I mentioned, it also fits into the fin support structure, which extends another, it's about 14 inches up into the booster. So it has quite a bit of support holding it in. And then as far as the thrust plate goes on the aft end, that's epoxied in place as well.
Okay.
It's also worth noting, we have compression tested another sample of this boat tail to 1,300 pounds with no failure.
Yeah, so we have at least a 1.7 times safety factor in compression.
Yeah, the reason what I'm really asking is, it's not just epoxied in place, right?
It is just epoxied, but there's quite a few locations and components that it's epoxied to.
Because, you know, PETG, you don't end up with a chemical bond. You just have the mechanical bond with any roughness in the surface. Epoxy doesn't stick to it.
Well, it's also worth noting that what this is really going to be bearing is compression, and the epoxy isn't really helping resist compression. It's really just the force going through that lip and the edges of the body.
Okay.
Like I mentioned earlier, we have a machined aluminum nose tip, and that fits into a 1/4-inch threaded rod that then in turn fits into a weight-reduced aluminum bulkhead. And this just kind of acts to compress the nose cone tip into the nose cone, and the bulkhead goes up, and they hold each other in place. And then we do epoxy that nose cone bulkhead just for some added security. Oh, we do have a slide, I'm sorry, for the breastplate motor retainer. So these are also machined aluminum components. They sit on the aft end of the boat tail I was talking about. And then we run FEA on both the thrust plate to make sure it has an adequate safety factor. And the motor retainer itself is held on with 440 cap screws. And you see a cross section right there.
Yeah. And if I'm reading the figure correctly, it's actually retaining the boat tail as well. Is the purple is the boat tail?
Yeah.
Yes.
What is the tan here?
The tan shade is our motor casing, or the more yellow. I might have misinterpreted. The yellow tone is our motor retainer itself. The sort of
right.
orange.
So the gray is the motor. Or is what is the gray here?
That's just the internal surface of our mock-up motor casing.
Okay, so that's, and then outside of the gray, the first layer of yellowish tannish.
I believe that's it's the cross-sectional cut of the motor casing. Excuse me.
Okay, that's the motor casing. And then outside that, there's some gray. Darker gray.
Sorry, I'm not sure. I think that's just an airspace between the motor casing and the motor retainer.
Okay, yeah, that's what I saw you were pointing at there.
Okay.
And outside that airspace, there's a slightly lighter tan.
Yes, that is the motor retainer.
Okay, that's motor retainer. And then the light purple is the boat tail.
Yep.
And then there's another layer of yellow here.
That is, yeah, that's the other side of the holes for the motor retainer. And the other shade of purple there too is our fasteners.
Okay, and so that serves to retain the boat tail as well. And in fact, you're
it's not retaining the boat tail, it's just retaining the casing into the, I suppose, into the boat tail.
But the boat tail itself.
The boat tail itself is not extruded by that.
okay. It looks like the boat tail on the image here is down from the retainer, which means in practice it's up from the retainer, right?
I'm sorry, I'm not really understanding the question. I could show the actual.
Oh, I think I might understand where there might be miscommunication here. So if we're imagining the actual rocket itself, if the nose cone is pointing straight up, invert the rocket. That's the orientation that we're viewing this from at the moment.
Right.
So the boat tail itself, we're looking at the 4-inch end diameter of the boat tail, and I can turn it over to them so they can actually show you, but it's the other side of the boat tail not pictured here. That's the epoxied surface. So
Right.
that's what's retaining the boat tail, and by extension, the motor retainer and the motor casing as well. But
Okay,
I can turn
well,
it over to them for more clarification.
let's just remember to return to that when we are looking at the actual rocket later.
Okay.
And continue for now.
Sounds like a plan.
So this is just the FEA results for our press plate here. You can see that we have a safety factor of above 15 throughout the entire part.
So, as Donovan will explain later, we have an equation to calculate the drag force. However, it works under the assumption that parachutes completely inflate instantaneously, which leads to a bunch of over designing of different parts. So in order to get a more accurate representation of what the stats force actually is, this year we've decided to implement strain gauges onto the forward bulkhead. They're going to be arranged in a half Wheatstone bridge configuration with 2 extra strain gauges to work as temperature correction in order to measure strain and then calculate the force that is affiliated with that.
Cool. I like that.
Thank you.
So for actually measuring the snatch force, we actually design our own board because the issue is it's such a small voltage we actually get. And since, as Lexi kind of alluded to, we decided to put strain gauges on our actual bulkhead and not risk the load path going through a load cell, which is not rated for these high shocks. We actually designed our bulkhead to just deform with the strain gauges, and that's such a small voltage, we actually had to design our own SRAD board. This is the board. It stands for, it's called Potato. It stands for Parachute Opening and Timing Observer. Basically, it goes ahead and takes the difference in voltage, as you can see on the moving camera, from the actual strain of the strain gauges, and then amplifies it, filters it, and then it sends it off to an onboard computer that'll store it via flight, as well as send it over to our modular flight computer in the Avionics bay.
Okay.
We have done some compression testing though, and we found a little bit of hysteresis, but it's also been able to be calibrated for this test model. And we don't have it currently in our rocket, but we are in the process of cleaning the surface and prepping it to be installed on the flight hardware.
Okay.
All right, so moving into the analysis section, we did a lot of open rocket simulations this year after last year's very windy launches. We wanted to make sure that our rocket would be okay in high wind conditions, as opposed to last year where we did it in the default wind condition, which is 5 miles an hour, and didn't really play around with higher wind speeds like we had experienced actually at the launch site. So this year, as you can see, there's different cases labeled. So I have them starting at 0, going up to 30. Obviously, we're not planning to launch in 30-mile-an-hour winds. That was more.
That's right. You're not.
No, definitely not. So a couple things to point out with this. Our speed off the rod right now is about 92 feet per second. So based on NARS launching safely in the 21st century article of having a rod speed of 4 times the wind speed, our go, no-go wind speed is roughly 16 miles an hour right now. We're also looking at an apogee of between 11,500 feet and 12,000 feet. That's likely to go down. We have most of our masses finalized, but obviously with integration and as we get closer, we're going to reweigh things and we're likely to add more mass. We also have more mass added in for stability in the nose cone, which is the small blob that you can see under the bulkhead in that nose cone. And that's a modular set of masses. So based on the final weights right before we go to the pad, we can screw or unscrew steel discs to the threaded rod to make sure that we still have a stability adequate for flight.
Okay. You will want to be very careful to have a good justification that 92 feet per second is going to be adequate.
Yep.
And you'll want to be able to point to that article, because That's not absurdly below the 100 foot per second that Ezra wants, but it is below it.
Mhm.
Sort of, if you'd hit 100, then no one would say a word. At 92, you will need to make sure you can justify that you will
Yep.
be safe.
So
We
we
do
have
al-
that article with justification, and we also have a slide coming up with justification that we're
Okay.
okay at that launch speed.
And the other thing is we do have a mobile weather station that we can use to know the wind live, so that when we get called up to launch, we can make that decision then, according to the actual wind speed at the time.
Okay.
So one of our justifications and the things that we were doing this year is looking at our stability and angle of attack off the rod, because one of the main failure modes last year with Kong was as soon as it left the rod, it canted by about 30 degrees, significantly impacting the flight profile.
Yeah,
I'm sorry?
I said, yeah.
So what we wanted to do this year was make sure that wouldn't happen. So we look at our stability off the rod is cal and a quarter, which is pretty good. So, and then also the angle of attack is 7.5 degrees, which also referring back to that launching safely in the 21st century article, under 15-degree angle of attack, your stability needs to be within the okay margin. We're very much under 15 degrees at half of that, and we still have an adequate stability.
Okay, I want to give me just a second to look something up here. Did you say your stability margin is about 1.25 calibers?
Right off the rod, yeah. And then it goes and it reaches its max at about 3.25, 3.25.
Okay.
That's a little cut off in this figure,
The
but what Open Rocket will do.
one issue here is the DTAG wants 1.5 calibers.
Okay.
Now you mentioned you have some weights that you can put on to adjust the center of gravity.
Mhm.
You know, are you going to be able to get to 1.5?
I believe so. We'd have to add probably one more disc, but it's not too much of an issue. We have plenty of extra stock, and we can just get a longer threaded rod to put that on.
Okay. Yeah, I'm looking here at your slide with showing launch rod clearance. Let's see, your stability margin hits 1.5. Oh, I'm sorry. I'm looking at. Okay. Now I'm seeing correctly. So you hit 1.5 at roughly half a second, and that's just
A little less. It's about a quarter second to a third of a second there.
okay. But that's looks like 0.2 seconds off after you've cleared the launch rail.
Roughly, yeah.
Yeah, and that's the sort of thing you can point to, that when you're in flight, it'll be at 1.5.
Mhm.
But you will,
Okay.
but that or putting on that extra weight is, you're going to want to do that to meet that requirement.
So would you recommend adding the extra weight and lowering our off the rod velocity more, or leaving it as is and pointing to that we're going to reach the 1.5 very soon after we leave the rod?
I would say, because your velocity is already low, you should probably point out when you're going to hit 1.5, and then you know, if you end up talking to Ken Overton, ask what he wants you to do. He's the RSO. He's the guy who actually says go or no go.
All right.
Okay.
Awesome. If that's all, we can, okay, yep, perfect. So next, moving on. So using the average wind case of 10 miles an hour, which is hopefully what we're going to be experiencing, at least somewhere around that. Our apogee is about 11,700 feet with a max velocity of just over 1,000 feet per second and a max acceleration of 420 feet per second squared.
Mm-hmm.
This is the fin flutter slide that we already went over, but using that max velocity of 1,048 feet per second and our fin flutter velocity, which is calculated to be roughly 1,456 feet per second, we have a very adequate safety margin of about 39%.
Mhm.
Looking at the snatch force, so Lexi touched on this earlier, talking about the strain gauge, about how this is technically a physically impossible calculation because it does assume that the parachute reaches its full drag area instantaneously, which won't happen. But it's a good upper bound for safety factor.
Right.
So right now we're looking to experience, if we launch at 0 winds, about 2,000 newtons of snatch force. If we launch in 25-mile-an-hour winds, about 2,300 newtons of snatch force. So we use the 25-mile-an-hour case as our safety factor upper bound, because if our components can survive that with a high safety factor, there's no reason to expect that they wouldn't survive at 10 or 15-mile-an-hour winds.
Right.
And then this snatch force gets distributed between the two sections of the rocket. So looking at how much gets distributed to each eye bolt and that bulkhead, we have about 50% of the mass, I'm sorry, 50.5% of the mass in the upper section. And that's because we added the extra masses in the middle, so it gets a little bit heavier. And so we're expecting that to experience about 257 pound force, 262 pound force, 1167 newtons of the snatch force. And then the booster section will experience 257 pounds, roughly 1142 newtons of snatch force.
Mm-hmm.
Looking at a railguide placement, so one of your feedback points for our second progress update was we should look into moving the railguide A, that forward railguide, back a little bit to increase our effective rod length. We did move it back about 3 inches from where it was. However, we can't move it back any further because that's used, as you can see, the mass component that's right inside that part of the rocket is our payload. And so that rail guide, and it's not on the inside of the rocket, is used as keying geometry for the payload. So that's as far back as we can move it without significantly impacting the payload design.
Okay.
So leaving it there, we're expecting, if we hold it, horizontally with no motor, to do that rail guide test, 49 pounds on that rail guide, 6 pounds on the other one for no propellant mass of roughly 55 pounds of the rocket.
Mm-hmm.
Moving on to Avionics.
So for our flight computers, we're using RIC3, which we're just reusing the one from last year because those are flight tested, and we also have backups. We retested them and they verified they're still functioning. We're also flying the same style tracker, which is a Big Red Beat. We know this tracker pretty well. We've kind of applied just reusing the hardware. We know the hardware. Yep. For our wiring diagram, because we have we're connecting everything through DE9s to our deployment bay. We have two separate DE9s which both charge paths go through, where the signal goes through both DE9s in case of a failure of a single DE9. That way we can ensure that both the signals from each computer gets to a sender to sender and a charge cup.
Okay.
So that is to say, we lose no redundancy even if a single charge line fails.
Right. Backing up just a second. You say lithium ion. You do not mean LiPo, right? You mean lithium ion.
Yes.
Okay.
We have 18650 cells we've arranged in that various 2S or 1S setups. For the bridge wires, this is a more detailed shot. It shows, like you have said, that we actually do have ensure that even if we do lose D9, we still have dual redundancy.
Mm-hmm.
For the structure, we made the entire thing of Delrin this year, and that's to basically because it's easy to machine, it's easy to laser cut, and it's fairly low friction. So sliding things together is pretty seamless, but also it's not going to wear out from the friction of moving things back and forth, and our slides aren't going to get damaged in fatigue of actual assembly.
We used to use plywood because it's very cheap and structurally good enough, but over repeated assembly, it starts to become a problem.
Right.
As I mentioned earlier, we're using a combination of 18650s and other Lion cells because of the no LiPo requirements this year.
Mm-hmm.
For our modular flight computer, we're using 2S2P, which shares its charge with the camera system we have on board. and the strain gauge measuring system. And then that one S cell you see on the right is for our big red bee GPS tracker. And on the left, we have just the same commercial off the shelf big batteries we buy for our flight computers to ensure that they're all COTS hardware. For our analysis of our structure, we basically assume the instantaneous force of the boost, and then from there looked at the weight of the ab bay and applied those forces to our joints. Since our ab bay has all the weight of the sleds on the end cap, we assume the worst case where it's pushing down on the little load tracks there. And from there we can then run analysis and figure out factors of safety. We went ahead and found a factor of safety of 3.16 for our 200 Newton load of the entirety of the weight of the ab bay, which was already an overestimate from what it's come out to currently. Following the load path up, we can look at the analysis of the weight of the ab bay on the long side part. This is the original model with the thinner pieces. We thickened them up just to ensure that they can be a little bit more durable and also like survive a drop test off a table in case that happens. And this had a factor of safety well over 15, so we're not concerned with that failing in tension. For our vent holes, we actually just used the RC3 formula. I've just formatted it nicely here so we can look at different parts. We are using 4 vent holes, and then the 5th vent hole is the size of our camera mount. Our camera mount is just further back, so we actually get the venting properties there, as well as all the other additional ports for our screw terminals and everything. Basically comes out to a bunch of 4 quarter-inch holes, and then slight camera holes of 3/8 hole that's slightly obscured with our screw holes.
Moving on to recovery.
All right. So that's just a quick diagram of the recovery harness setup. As you mentioned earlier, we're using a single bay dual deploy system. So we have a main parachute, which is constrained within a parachute bag, and we have a drogue streamer. That main parachute bag is fixed or is constrained to be within this upper section of the rocket. We do that so that the airstream won't cause the main parachute to come out too early, and we can make sure we don't have a main apogee event. Other couple of important note, one of the things you mentioned in one of our progress reports is your concerns about if both TD2s successfully separate, we'll lose a portion of TD2. There is a line that runs from the middle of the TD2s to a loop that goes around the main line. I mean, that's there, so if both TD2s separate, you can save that middle section. We aren't losing anything into the desert. We also have a diagram and a couple slides that goes into that in more detail. For deployment phases, as you can see on the far left, when we are under streamer, the red line is our tension path. And so that's going to run through the TD2s, and it's going to stay out of the way of the main parachute or the main line. When we separate the TD2s, that load path transitions to the main line, which is under slack when the streamer is deployed. By doing that, by separating the shorter line, we then move the tension over to that main line, which starts extending. And as it extends, it exceeds the length of the shroud lines of the main parachute, causing the main parachute to get pulled out of the parachute bag and deploy. All right. And here's that diagram I was talking about earlier about the TD2 deployment scenarios. So you can see on the left side, if both TD2s fire, then our restraining line keeps those TD2s attached to the rocket, but allows them to fully separate. That loop is sized such that it can freely slide up and down the main line, but we won't lose the TD2s. If only the upper TD2, or sorry, only the lower TD2 fires, then that restraining line stays within the stays within the upper section of the rocket. It doesn't do anything, won't get in the way. And then if only the upper TD2 fires, then that constraining line will move out of the rocket, but would still stay out of the way. And we have pull tested this to ensure that this does not cause a problem. All right, our main parachute is a 12-foot diameter chute from Rocketman, slows the descent down to about 20 feet per second. Our streamer is a student manufactured streamer of 112 feet long and about 8 1/4 inches wide. For simulating this streamer, we use the same drag coefficient of Rocketman's extreme streamers. This way we don't have to calculate our own coefficient of drag, and we can still do analysis on it effectively. And that slows the descent rate to about 65 feet per second.
And another concern, you actually have the parachute?
Yes,
Okay.
the whole recovery harness is integrated into the rocket at the moment, but we can open it up and look at it later.
Well, that's just another one where there's been some supply issues.
Yep. Yeah, we were able to reuse our parachute from last year, so we did not have an issue with that.
Okay.
Moving into some background information. Last year, our rocket Kong, the shot cord split in flight, and the booster section fell without a parachute and without a tracker into the desert. Fortunately, we were able to recover that, but in order to mitigate that failure from happening again, we added fox hunt beacons in both the upper and lower section of the rocket. This way we can radio locate both sections of the rocket independently if they separate, or we have two radio location beacons in the rocket if it falls down in one piece and we lose GPS.
Okay.
And finally, for our BP charging, charge sizing, we only need deployment charges for drogue because main deployment's controlled by the TD2s. And so we utilized a community source calculator that we have used in the past and deployment testing to ensure that our 6.6 gram primary and 10 gram secondary BP charges are sufficient.
And those are substantial black powder charges.
They are. We have a very large deployment bay because of the single bay design as well as the payload
Okay.
needs to exist in that bay.
Payload?
Where's that? There's a video of the deployment testing.
Yeah.
Yeah, well, I'd like.
Hold on. No, it's just not playing. There we go.
Maybe we're in.
So, because the fact that we deployed so that was the primary charge. We did not test the secondary charge. We decided that the primary charge can separate the rocket, and the secondary will be big enough because it's bigger.
Yeah.
The charge itself created enough force to deploy the payload, which is very promising. As well, you can see it started deploying the streamer. Immediately after that video ended, we went up and started pulling on it, on both the upper section and the booster. And just with slight pulling, the streamer came out and deployed successfully, but the main parachute did not. And so that was kind of a verification that our topology would work.
Mhm.
Moving on to our payload.
All right, so our payload's mission this year is going to be testing an SRAD reefing system. It's going to be a purely mechanical test, so we're not going to be implementing any custom PCBs for deployment of the reefing or disreefing. And we're going to be monitoring the snatch force on the parachute using a load cell. We'll be monitoring it both at deployment and at disreef to see the effects of it. That'll be monitored by our SRAD PCB, the Grim Reefer. The Grim Reefer, as I've said it before, we're using RRC3s and Piranha line cutters. So the Grim Reefer, despite its name, is not affecting the reefing system. It is only monitoring it and taking data for it. The reefing system itself is a modification of an existing hemispherical parachute to implement a reefing design that we took from a design manual published by the Navy. The main feature of it is a control line that you use to cinch the diameter of the parachute. And then whenever you want to disreef and allow it to open back up, you cut it somehow or release it somehow. And we chose Piranha line cutters for that. The payload's interface, we have a Sabo, which is going to interface the 3U format to the circular rocket. It's also going to help us line up our screw switch holes via keying geometry with the upper rail guide and a pin, a separate flight pin. After arming it, the flight pin will be removed and it'll be allowed to rest on top of the coupler between the two sections. And the rocket's shock cord will pass through the Sabo, giving it a line of contact so that we don't lose it, going through a design hole that has plenty of clearance. There will also be a static line connected to the rocket recovery harness to deploy the payload chute at a safe distance away from the rocket. The payload parachute is inside of a separate bag connected to that static line. The Sabo itself, here's a quick cat of it. Whenever we open it up, we can show you it in more detail. It has a thicker bottom to kind of prevent breaking with the force of the 8.8 pound payload pushing against it during deployment, as well as previously mentioned, keying geometry and venting geometry for the payload itself to make sure that all of our.
If we can go back a couple slides again, I am a little bit curious about your line cutters. And in particular, there's no way that you can end up with a piece of line coming loose in the desert, is there?
No.
Okay.
And the reason for that is because the reefing system, it uses two separate loops that are anchored into the parachute. And then the control line is connected to both of those loops simultaneously at a connection point in the middle. And then it is pulled
Okay.
downwards to the piranhas. So when it's cut, those will still be connected to the two loops that are anchored.
Okay.
Moving on to some analysis for the payload. We wanted to do some snatch force calculations just to make sure the payload and all of its recovery components can survive. Once again, using that same general drag force equation, that gives us a pretty solid overestimate. We gathered that in the worst case, if we disreef at apogee, this is assuming the reefing system will fail. We're hoping that it doesn't, and we've done a lot of mitigation to make sure that it doesn't happen. But in that case, we wanted to make sure that everything can survive, and that's where we're expecting a little over 1,000 newtons of force. And then moving on to the next slide. We did some FEA and we looked at the data sheet to spec our components to make sure it could withstand this force. So looking at the FEA, the recovery bay, which is made of steel, can very much take that force, as can the aluminum posts. The thing that's the most at risk here would be the load cell. So right now with that 200 kilograms, it's the full scale reading of the load cell. And that is when the sensor breaks. So not when the steel or the metal around the load cell itself will break. That's just when the sensor breaks. And since we couldn't find anything about when the physical part of the load cell will actually snap, we know that it's going to be higher than 200 kilograms. So if it's safe at the 200 kilograms, it will be safe at whenever that metal will actually snap. And the I-nut is also going to be safe at 1060 newtons.
Mm-hmm.
I believe this is the end of the presentation.
Yep.
Okay, this is looking like a very nice piece of work.
Thank you.
But
Thank
yeah,
you very
let's take a look at the rocket itself now.
Oh yeah, we have a camera.
Yes.
Yeah, should you turn the camera? Say everything.
It's already been.
Oh.
I'm gonna stop sharing.
Yeah, can we switch?
Yeah.
Oh,
Oh, yeah, it has to,
Okay.
it has to.
There we go.
Oh, that's weird.
Unfortunately, it has to be vertical, it seems.
That's unpleasant.
So where would you like to start?
At the nose.
All right.
So actually, what are you using for a tip protector there?
It's a crocheted wizard.
Ah,
Yeah.
It
I
has
like
some
it,
bone
yes.
sides so that we don't damage the crochet. This is to protect both the tip protector and the tip.
yeah,
And to
well,
protect people from the tip.
yeah, but that's its main purpose. All the teams seem to be coming up with fun tip protectors.
Okay.
So let's take a better look at the nose cone there. Got the nose cone.
We also
Um,
have the avionics bay inside of the nose cone right now, in case you want to look at that as well.
Sure. Let's pull it out and take a look.
All right.
It's easier to do with the drill. Hold this up and then rotate it, because there's the on the other side.
So we're just removing the two retaining screws for the avionics bay.
We tried to dress up the rocket for the demonstration as flight worthy as it can be.
Yeah,
Mhm.
based on the other videos, it looks like they want viewers want the rocket integrated. So
So in the inside here, we just have a piece of Delrin that goes down the line to line up for our FA to make it really easy to just slide it in and then put in the screws on the sides.
Okay,
And then at the very end there is our nose cone bulkhead that you can see.
right.
That also has the threaded rod where if we need to add more mass, we can just screw it onto the top right in there.
Right.
So here's our
And then you've
avionics.
got your avionics there.
Our connections come out through these two DE9 connectors, which will then go into our deployment. They go into the deployment bay at the bottom here. And then we additionally can have more DE9s to support the emission like strain gauge to connect to our modular flight computer over here. And then for
Okay.
taking the avionics apart, we just undo the threaded screws up here. And I need you to connect. You got to disconnect the other sled. Power.
Okay, and yeah, I don't need to take that apart. That's
Okay.
Yeah.
That's fine.
okay. So that goes up in the nose cone, and then you had the two screws holding it in the nose cone.
Yep. Through here and through here.
Mhm.
And
Okay.
all of our cards hardware sits on this sled right here. And the batteries are in the back. Inside
Right.
With our two switches and our camera that line up on the pole track on the side of the nose.
And then below that, you've got your deployment bay, I think you called it.
Yes, or sorry, the avionics side of the deployment bay, which is just the top of the bulkhead where we run these wires through. It's just
Right.
the bulkhead that's in there.
So I can angle this.
So in here, we have two holes right here by the bolts where we run through our wire and then we fill it with a caulk so we can get a good seal in there. And
Mhm.
that way we can get our charge wires in there. And additionally, this wire on the right here is for sending signals to our strain gauge measurement stuff.
Okay.
That's a nose go.
So that's the nose cone section, pretty much in full.
Okay, and so then there's
Here, I'm gonna let go to this side so you can see where you're.
I think I see a joint in the body just aft of the
Yep.
yeah.
So this is actually something that we implemented coming from last year. So last year we had a very long section of tube. Before you pull that out, we had a very long section of tube that you'd have to reach down to get to the deployment side of the bulkhead. And so this year we essentially took that long section and we broke it into still a long section, but then a much shorter section that splits right before the bulkhead to provide easy access to the deployment side. And so this does not separate in flight, but it's just held on with
Right.
3 M5 screws for easy access.
Okay.
So Alan's going to pull that out. We do have our whole
Yeah.
free
And
assembly in place.
so we'll start up at the top bulkhead. We got our two charge cups in here. That is where deployment charges will be. They're machined aluminum, and we make it this way just so we can prep the charges outside the rocket and then insert them into the rocket when we're ready for them. We do this just so it protects the charges a little bit better and it's a little safer, in my opinion. Moving up, we have this upper quick link. This quick link has our main line attached as well as the parachute bag and our TD2s. Everything is a little bit of a mess right now because of being pulled out.
And let's see your igniters for your black powder charges. Are they just coming up into the bottom of the charge wells?
Correct. There's little holes down here.
Right.
And they are big enough to run 2 E-matches through. And on the other side of the E-matches, there'll be a crimp connector so we can attach those directly into the aft bay.
So
Okay.
they run through those small holes there.
All right. From here, we got our main line as well as our retaining line for the TD2s. Got our flying blanket.
It's worth noting, this is not actually how it comes out of Apogee because this is the non-separating joint. It would come out over.
Yeah.
Yes.
Mhm.
We got our 2 TD2s. See how the retaining line's attached. So if we separate right here and we separate up here, this is going to come loose, but our line is attached such that this won't fall away from the rocket.
Okay.
I was going to start. Here we got the parachute bag coming out. Once again, this will be constrained in the rocket during flight. One of the main things we do is that when we Z-fold all of our shot cord, we put some just blue painter's tape around it. We do this so that it will stay together and it's really easy to integrate. But as soon as you put any force on this hinge tape breaks and the shock cord can unfurl.
Mhm.
This orange line right here is the static line that Brax mentioned earlier. This attaches up to a quick link right here. And so when the payload deploys, this line goes taut after about 15 feet of falling, 15 feet of payload falling, which pulls out the payload's parachute bag on the payload's parachute to deploy. Got the rest of our common line up here. This line is what runs through the payload and attaches to where the streamer mounts and the swivel link at the end of the rocket. This is there. We cannot see anything else up here, so if you're ready to move back to the actual
Yeah.
separation, we can look at that. So right here is where the rocket will separate in flight. Yeah, get that light full. So when the rocket separates, as you can see that, on that payload. Oh, be careful where it doesn't fall apart. Yep. Oh, so as you can see from that deployment test, the Sabo comes out. And as the Sabo comes out, it just opens up and unfurls. Done. All right. If you want to look at the Sabo, the payload in Sabo right now, we can, or we can keep looking at the recovery.
Now, is there something positive opening up those petals on the Sabo?
There is not. But from our deployment test that we looked at, the payload will open up these petals because it'll be sideways and everything just kind of falls out.
The pedals are only together because they're inside a tube, but once it's outside a tube, like they're not holding up 8 pounds of payload.
Okay.
All right.
I wonder if it'd be worth putting like a spring.
We can consider that. However, we have used very similar payload Sabo designs in the past, and every time our payload has deployed successfully.
Okay.
Do those hinges stay attached? I mean, that one of my concerns would be that one of the sides would come off of that.
So if you see down on the bottom, you can show there's 2 holes. They're not currently in right now, but shock cord passes through those holes
Okay.
and connects all of them to the base plate.
Okay,
And
that's
so
much better.
there's dual redundancy for those hinges.
Great.
All right. Below the payload, we have where the swivel link connects as well as the streamer. The streamer is attached above the swivel link. That way, if we do have a spin while under streamer, the swivel link will hopefully negate some of that. Pull the streamer out real fast. The way the streamer is folded is it's Z-folded for all 100 feet of it, and we roll it up into a little burrito. And so this is just so as soon as it comes undone like this, all that Z-folding can come undone and the streamer can deploy.
Mhm.
Below the swivel link, we got what I call the riser line. This is just an extra set of shock cord to help mitigate the force of deployment, as well as add some extra length so the booster and upper section of the rocket don't hit each other under streamer or main parachute. And finally, all at the end is the quick link and the eye bolts.
Can I take a look at those loops on your shock cord?
Right here?
Yes.
Yeah. What kind of knot is that?
Palomar knots. And they have been tested, and I have this source somewhere to preserve 90% strength of the cord.
Okay. And I didn't hear what knot is it?
A Palomar knot.
Okay.
It's a type of fishing knot. But we've
I've always heard it pronounced Palomar, so I missed it the first time you said it.
Oh,
This team is the only place I have heard that's Palomar.
Okay.
How was it pronounced?
How?
Oh,
Okay.
That's how everyone said
James
it.
said it as
Fishing.
Palomar, and then Alan said it as Palomar.
Yeah.
Now we're stuck.
Yeah.
all right. That is it for the recovery harness. So is there anything else you want to take a look at? I'll hand it off to somebody else.
Not on that, no. Let's keep on heading south
So,
or aft.
yeah, actually, one thing we should point out real quick, moving back up the rocket to our upper body tube. If we look at the aft end of our bulkhead, we have not actually placed the strain gauges yet. I'm sorry, it'll be on the opposite side here. But we have two
Mhm.
surfaces. So on two of these spars, we would place two of our load reading strain gauges. And then two more strain gauges would be placed on the flat surface that's sort of indented in here. And those are just to complete our bridge.
And we have the test bulkhead right here as well.
Yeah, we do have an example of our test bulkhead that we've put through the compression tester. So these are the two strain gauges that are actually reading strain, and then these other two are placed here for balancing reasons.
Right.
So we haven't put these on the actual rocket quite yet, but we'll be doing that the upcoming week.
Okay.
And then moving down to the last section of our rocket, which we just call the booster. I guess the only things to note here is our fins. We have a fin fillet running along both edges of where the fin contacts the buddy. Here's our aft rail rod, sorry.
Mhm.
And then at the aft end of our boat tail, we have our motor retainer and our thrust plate. They're both bolted together right now with 6 440 screws. We don't have our motor casing in right now. This is actually an older one, but it's the same size diameter, so we've used that to do some test fitting.
Okay. And that you know, that figure earlier showing the boat tail and the retainer. Yeah, that's showing me I was reading it correctly. And yeah, that retainer is also retaining the boat tail.
Okay.
You mean retaining the boat tail in the rocket?
Well, keeping the boat tail from falling off. Yeah.
Well, there's nothing between the motor retainer and thrust plate and the rocket other than the boat tail. So I guess I'm not really following that. There's this tube in here, but this is not.
I've seen quite a few boat tails designed, so they are completely on the outside of the retainer. And so there's nothing but the epoxy holding them in place. And where PETG, the epoxy doesn't actually stick to it, I would be concerned about the boat tail falling off. In this case, because the boat tail is, constrained by your motor retainer, it would have to go through the motor retainer to fall off.
The motor retainer screws into the boat tail, or the thrust plate is epoxy to the boat tail, and the motor retainer screws into the thrust plate. So it is just an epoxy connection cube holding the boat tail.
Yeah, these maybe I'm not being clear, but these little screws here, they terminate right around here. They don't actually connect to the boat tail itself.
Oh.
Yeah, that's just to hold the motor retainer onto the thrust plate.
Okay, in that case, there is room for concern.
I suppose I can say that we will look into it, but this is a very similar design to what we used last year with success.
Okay.
We're not running, this component is mostly in compression. The only time that it's really under any sort of tension is holding the weight of the motor itself before launch.
How about when it's deployed? When the recovery system's deployed?
I'm not sure I'm following. I'm sorry.
Oh, I see. Yes. So yeah, when the recovery system deploys, it needs to restrain the motor. Yeah.
Right.
Oh, just the mass, the inertia.
Just the
Okay.
inertia.
I see.
Right.
Okay, I suppose the only thing I can really say for now is that we'll look into it, but I appreciate you bringing up the concern.
Of course, this is a plug motor, so it's got a threaded front closure. How hard would it be to put a threaded rod into that?
It would be somewhat difficult if I'm being honest. It probably
Okay.
could be done if we really had to. We could design a new component to fit into this end, but it would be somewhat difficult.
Yeah. See if you can find a way to get a better mechanical connection on that from the boat tail to the airframe.
Okay. I suppose maybe one mitigation we could do would be to drill holes through the body tube into the boat tail itself to sort of retain it in a similar way to a coupler tube.
That would do it. Yeah, that.
Something we could look into.
Yeah. What else to think about? Oh, by the way, the my amusement when you mentioned the fin section landing in the desert last year. Is a
Yes.
couple months ago, I recovered a fin section that I had lost in the desert down here 9 years ago.
Wow.
We can find boys.
Yeah, we have
So-
our Kong over there was from last
Yeah,
year.
let's.
We could actually take a look at that and search for pineapple. So
Yeah.
I'm not sure how the audio is over here, but.
It's not.
Yeah, so this is it falling from 7,000 feet without a parachute.
Yeah.
It held up,
Stout.
I have to say it held up reasonably well, given that, but we've reinforced the fin section against falling from 7,000 feet this year.
Good. Okay, I'm trying to think if there's anything else I want to bring up. This is a very nice piece of work. I am really looking forward to seeing you guys at Spaceport.
Thank you.
Thank you very
Um,
much.
Thank you.
Just there were the 3 things that came to mind going over this, and one is your velocity off the rail. Second is your stability margin, and third is that boat tail retention. So I'd say check into those, and then I think you're ready to go.
All right, thank you very much.
Sounds great. We'll definitely follow up on that and make sure to correct those. And we'll reach out if we have any questions throughout the process.
I just thought of something else. That's 1 1/4 calibers. What's your percentage stability margin?
I'm unfamiliar with what you mean by that. I've never really heard of stability measured in percentage.
Oh, percentage of the length of the rocket.
Um,
So if your rocket's got a fineness of 10, then 1 caliber is 10%. If your fineness is 20, then 1 caliber is 5%.
okay.
But actually, yeah, that your rocket is more than 10 to 1, and so I was hoping that it was going to turn out that your stability margin in percentage of rocket length was going to be greater than 15%, but that's not going to happen.
No, definitely not.
Which version of OpenRocket are you using?
23.09.
Okay, and there's a setting in your preferences that you can have it tell you calibers, percentage, or both for your stability margin.
And so for percentage stability margin, the range we should look for is about 15.
Right.
Okay.
There's quite a few people, and I'm actually one of them, thinking that the percentage of length is a better measure than calibers,
Okay. Interesting.
because when you have one of these long, skinny super rocks, then 1 caliber is not very stable.
Right.
When you've got short, stubby little thing, then 1 caliber is really stable. It seems like the percentage of length is a better measure.
Okay. Yeah, we can absolutely look into that.
Okay. Well, great. I believe the next thing is you were supposed to send me a link to the recording of this, and I'm supposed to pass it on to somebody, and so we can take care of that next. And thank you very much for your time.
Absolutely. Thank you very much for spending the time with us. We really appreciate your feedback. We're going to take a look at all those feedback points and make sure that we address it. In the meantime, it'll take a second for the cloud to process the video, but we'll get that over to you as soon as possible.
Okay. Thanks a lot.
Awesome. Thank you so much.
You bet.
I have one question about the stability. That percentage of length, is that really just an abstraction for the mass moment of the rocket? Because if so, then our mass moment should be much lower than the length suggests, since so much of our mass is the payload, which is right at our CG, or like right at the pivot point.
And I would have to think about that. I believe the answer is no. That it is just a different measurement of CG versus CP.
But in terms of the impact of the corrective moment on the rocket, it has a larger impact if the mass moment is lower. And the mass moment in this case, it's not the mass moment of a uniform rocket because so much of the mass is right at the CG.
Right.
Because I've always thought that the calibers is just like some reasonably well correlated thing to the length of the rocket, because they're not like the aspect ratio doesn't change too much, and which in turn is an abstraction of mass moment.
Yeah.
It's something to look into, I guess. Yeah.
Yeah, you're right. The mass moment is going to be smaller because it's because all the mass is at the middle, is at the CG.
We have some additional mass at the nose, but it's not. It's by no means uniform throughout the rocket.
Right.
Most of the mass.
And yeah, so because of that, it'll be an argument. It would be an interesting argument to make to see if it would actually fly. But I can see that. Yeah, fewer. A smaller stability margin would be safer with a smaller mass moment. The amusing thing there is I just rewrote most of the mass moment calculations in OpenRocket a few months ago.
Nice.
Yeah, actually, I think that is we can get that from the simulation output, like over the so. Yeah, we will definitely look into that. Thank you.
Yeah.
Awesome. Any other questions that from any of our members or from Sam Feinberg, who's our flyer of record?
I'm good.
Okay.
Yeah. So am I.
Awesome. Sounds great.
Have a
Huge
good
thanks
day.
to everybody.
Thanks.
Really appreciate your time. Thank you.
Thank you.
Thank you. Bye-bye.